recorded.
And now let me remember what to do. I say share screen, and I go to iPad, and then I got to do mirroring. Okay, folks, you can see this, I think. So today the discussion will be addition of angular momentum, or I'm sorry, of spin angular momentum. That's the main topic for today. Can you see that okay? And hear me all right? Just do a thumbs up or something. Yeah, okay. Yeah. Good. Okay, good. All right. So let's dive into it then. Let's see. So last time we were talking about the many-body wave function, and we were talking about how we can have a spatial part, which is a function of the position of all the particles. But we also can have a spin part, which is going to be a function of all the spin. Let's say if it's a bunch of electrons, the z component of the spin of electron 1, of electron 2, electron 3, etc. And so what I want to focus on today is this part, the spin part, because we've already talked about the spatial part quite a bit. So let's talk about the spin part. And so the question is, how do I think of this, the many-body spin wave function, many-body spin wave function? And so we already sort of started this discussion, and we know that the simplest thing is that we just think of it as a product state. And that's a pretty natural thing to do, because we know that if we have particle number 1, then we know that its state can be S1 M sub S1, where this is the eigenstate of the S1 squared operator, and this is the eigenstate of the eigenvalue, the quantum number for the S1Z component operator. And then if I have particle number 2, then similarly its spin state can be S2 M sub S2, and then similarly for particle number 3, we would have S3 M sub S3, and then of course we can write a product state, a total spin wave function, which I'll just call chi. We can write that as the product state of all of these guys. S1, M sub S1, S2, M sub S2, etc. And I think that's a very sort of natural thing to do. You say that the total spin part of the wave function for the many-body system is just going to be the product of the spin states of all the individual particles. And that I think that's a very logical thing to do. And then you can do things, for example, you can realize, you can ask something like, you can say, what's the dimension of this state? How many states? How many states? In other words, you could say something like, what is the dimension of the Hilbert space? Dimension of the Hilbert space. Because I think this is very simple and intuitive, but if you sort of look at the mathematics behind it, it's really the mathematics, it's really linear algebra. You know, the mathematics of quantum mechanics is mathematics of linear algebra. It's exactly linear algebra. And so we can think of this as so some language that you would use in linear algebra, and I'm not like a big mathematics whiz, but it's just sort of the language that people use. You could say that I have this. I can think of this this spin. I can think of having the spin state of particle number one, and I can have a tensor product of the spin state. So we think of this as a tensor product. If you're used to that language, this is the language of linear algebra. And so that's the spin state of particle one, and this is the spin state of particle two. And I have a tensor product, etc. And I can go on and on. Particle three, etc. And so how many spin states are there for particle one? Can someone tell me? For particle one, if it's a electron, let's just talk about electrons for now.
2.
Yeah, exactly. There's 2 states because it's spin up and spin down. So we have 2 states. And then, of course, for particle 2, it's the same thing, 2 states. And so we can think of, and so using this abstract language of Hilbert space, we can say that the Hilbert space for spin states of a single electron, then we could say that the Hilbert space has dimension equals to 2. It's just a 2-dimensional Hilbert space because there's 2 possibilities, there's 2 basis states. And the same thing here for particle 2, particle 3, etc. But then we can ask, okay, well, but what's the Hilbert space of the many-body wave function? What's the Hilbert space dimension for the many-body spin wave function? How many states can it have? And so let's say, so if I had 3 particles, how many states? Somebody tell me.
8.
Yeah, exactly. Because it's going to be 2 times 2 times 2 times 2, etc. So for each particle, so then we're going to have 2 to the n states, where n is equal to the number of particles. Okay, so there's a lot of states there. So there's a lot of and these states, of course, right now are product states, right? Simple product states. And so if I go to the simplest example and I say that I have two electrons, then how many, and if I say chi is the spin state, then how many possible states are there for 2 electrons? How many possible spin states?
4.
Yeah, exactly, 4 is equal to 2 times 2. So this is the dimension of the Hilbert space. I mean, I'm being a little sloppy in my language. I mean, because the number of possible states is infinite, because I could say I have 1/1,000,000th of up and 1 and 999,000ths of down, and I can construct arbitrary superpositions, but I'm talking about how many basis states. What is the dimension of the Hilbert space? That's what I'm talking about. And then it's really simple. So it's the dimension of the Hilbert space is equal to 4. Okay, now that makes a lot of sense. And I think this part is very intuitive. And what we're doing is basically for the product states are eigenstates. The product states we've just been talking about are eigenstates of what operators? Well, they're the eigenstates of S1 squared, S2 squared, S3 squared, etc. And at the same time, S1, Z, and S2Z, S3Z, etc. So the product states are eigenstates of all these operators. So so I'll just say the product states are eigenstates of these operators. But a very important point is that there are other possible bases, other spin bases exist. Other spin bases exist. And we can do a basis, and so as a result, that means we can change basis. Change basis. So we can go to another basis, and what does that mean? Change basis. I mean, you've done it before, and it's a linear algebra concept, but it basically means if we're talking about a basis, then what it means to be in a basis, it means that we express our states in terms of the eigenstates of a certain set of operators. Express states as linear superpositions of some set of eigenstates. Well, I'll write it like this: of eigenstates of some operator or set of operators. And so you can see how we did that already. So for the simple product state, we chose to express our spin states in terms of the eigenstates of these operators right here that I'm pointing my arrow at, these guys. But what if I choose to express my spin states in terms of the eigenstates of a different set of operators? That is what a change of basis is. It just means rather than expressing my states in terms of the eigenstates of one set of operators, I'm going to express my eigenstates, I'm going to express my state, my wave function, my states, in terms of the eigenstates of a different set of operators. So it's kind of a simple concept, but it's one of those simple things that can be kind of confusing. So what is a different set of spin operators? Different set of spin operators that we can use to express our many-body spin states. So the simplest ones are the ones we have up here, just S1, S2, and S1 squared, S2 squared, S3 squared, S1Z, S2Z. Those are the simplest ones. But we can choose a different set of spin operators and we can write our states in terms of the eigenstates as a different set of spin operators. Can someone tell me what is a different set of spin operators? Tell me, someone. Just shout out.
The total spin?
Yeah, exactly. Total spin. Because I could say, let's define. So I can just, out of the blue, I can just say, let's define a new operator. Let's define S total. That's a vector, and it's an operator, as S1 plus S2 plus S3 plus dot, 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 dot. So let's just define this new operator as a total spin is equal to the spin of all the different particles. It's a new operator. And then similarly, I can define the total Z component, and it's an operator. I'll put a little hat, it's an operator, and it's going to be S1Z plus S2Z plus S3Z. Okay, and so I've just defined a new set of operators, these two operators. And if you look at these two operators, it's actually a much more compact kind of notation, because now I only have two operators, whereas before I had, here I have 2n. If n is the number of particles, now before we had here 2n operators. And so now if I define these new operators, the first thing you can ask yourself is, what is the Hilbert space that they operate in? They're operators, they're they're like matrices, and what is the Hilbert space they operate in? And you can see that it's the same Hilbert space that we had before. Like if you look at the product states, then that Hilbert space, which is the tensor product of all those different individual spin states, you can see that these operators act in that same Hilbert space. And so that means that I should then be able to have a transformation of bases. I should be able to go from those product states, which are eigenstates of all those individual operators. Now I should be able to transform into the eigenstates of these new operators. And the point I want to make is that the dimensionality is the same. It's the same dimension. I'm operating in the same Hilbert space, but I'm just transforming from one set of eigenstates to a different set of eigenstates. And so then that begs the question, what are the eigenstates of these new operators? What are they? Okay, what are the eigenstates of these new operators? So, okay, so to answer that question, what we can do is we basically just go through the exact same logic that was used to define the eigenstates of spin. And I'm not going to go through it because you went through it last semester. It's the exact same logic that you first were introduced last semester to find the eigenstates of orbital angular momentum. Then we used that same algebra operator notation to figure out the eigenstates of spin. And now we're going to use that same exact reasoning to find the eigenstates of S total. Okay, and so I'm just going to sort of go through it rapidly, really rapidly. So let's do a lightning review of that logic. So the logic is that what we do to find the eigenstates of these weird new operators, what we do is we can just say, well, let's define S total squared, and that'll be S total dot S total. That's going to be then S1 plus S2 plus S3 dotted into that same guy. You can see I'm not really into using elegant mathematical notation. I just write everything out. I think, elegance I find confusing. Okay, and so then at the same time, of course, so we define this new operator as total squared, and then we can do things like we can start looking at the commutators, and then we notice that we can start noticing things like S total X and S total Y. If we look at the commutator, it's going to be equal to IH bar S total Z. And so we notice that the components of the S total operator don't commute, and that's really easy to figure out. And it's a homework problem. And then we can do other things, like we can notice that the commutator of S total squared and S total Z do commute. Oh my God, they commute. And so this should look very familiar to you. This is just the same argument that we went for before for angular momentum. And so then we say, okay, well, these guys commute. So that means that we can have simultaneous eigenstates of these two operators. And so then therefore, there must exist eigenstates that look like this, and I'll call them S total, M sub S total. So these things must exist, where these are simultaneous eigenstates of S total squared and SZ. So these simultaneous eigenstates must exist, and I will call them this. And so that means then that S total squared acting on S total M, I'll just call it, this is really tough notation, I'm just going to call it M total like that. Then this must equal some lambda, I'll call it lambda S squared, S total, M total. And similarly, S total Z acting on that must equal some eigenvalue of SZ, S total, M total. Okay, it's the same reasoning, and then you can say, okay, but what the heck are these eigenvalues? lambda s squared, what is that? And lambda s of z, what is that? And so to figure out what those eigenvalues are, you can go through the same logic that you went before, where what you can do is you can define raising and lowering operators. Just like you did before for angular momentum. And we can define them like this. We can now define them for the total spin. We can say, let's define S total plus as a raising operator, and let's just call it, I'm just defining it. I can define anything. S total X plus I S total Y. Oops. Get this right. The Y component of the S total vector, and then I can define, these are operators, and then I can define S total, the lowering operator, so I'll call that a raising operator, and I can define my lowering operator, S total X minus I S total Y, that'll be my lowering operator, and then we can do some clever math, which you guys did last semester, and it's very easy, it's very straightforward to show that if I take S total, my raising operator, and I act on it on S total, M total, then it's going to equal some constant times a new state. And can someone tell me what that new state is? Someone tell me what the new state is?
Is it S M plus 1?
Exactly. S total, M total plus 1. Yeah, it raises the eigenvalue of SZ. It's raised. And then there's some constant living in there. And that constant, if you go through some muckety-muck algebra, you'll see that it's H bar times, let's see if I can fit on here, S total plus 1, S minus, oh shit, I forgot the square root, minus M total plus 1. Okay, and that's the constant that's out in front. Constant. And this is now that's the, to make it all normalized and everything. So, okay, so, and I'm just going fast on this because I'm assuming that you all have seen this before, that you all went through all of this and derived all of these things for spin and angular momentum last year. But the point I'm making is we can do it all over again. The algebra is exactly the same for total spin angular momentum. And so we can similarly define a total lowering operator. And we can, as I did already, I showed you that, but then we can act on that on a simultaneous total spin angular momentum eigenstate, and we see that it also then is equal to some constant, but now it has lowered the z component of the total angular momentum. Okay, and then there's some funky little constant there, and so let me write out the constant. It's h bar square root of S total plus 1 minus M total, oops, M total minus 1. Okay, so, and so this is now lowered. Okay, and so then what we can do is, by using these raising and lowering operators and showing that there has to be some upper limit and some lower limit, and screwing around with the algebra and using some clever mathematical logic, you then can show that the eigenstates, so then I'm going to skip a few steps, but I've shown you the important steps. Skip a few steps, and then we can show that S total squared acting on S total M total is equal to H bar squared times S total plus 1, S total, M total, where S total has to equal an integer or half integer. Okay, so you can prove that pretty easily, and you guys have all seen that proof last year. And then similarly, you can show that if I act SZ on this hypothetical eigenstate of total spin, then I can see that its eigenvalue is going to be H bar M total, S total, M total, where the possible values of M total, well, I'll ask you, what's the smallest value of M total? What's the smallest value of M total?
Negative S total?
Exactly, that's the rule. And the largest is then, of course, plus S total. Okay, so, all right. So this structure, really everything I've just derived here, really it all comes from the commutators. If you guys remember that derivation, really once you know the commutator, then boom, all of this algebra just falls out and everything I've written down is just a natural consequence. But and so it's all, so in some sense it's all sort of obvious. That's why it's in your homework problems and stuff. So it's obvious after you've thought about it, for a bunch of time. One of those things that's obvious once someone explains it to you. But now we want to ask the question, a more in-depth question is, how do we actually write the eigenstate? Okay. How do we write the eigenstate? Because remember, the whole point of this discussion is there's a change of basis. So we know the product states. The product states are really simple. S1, M1, S2, M2, S3, M3, etc. But how do I write? But the question now is, what is S total, M total in terms of product states? So the product states they form a basis. And how do I write S total, M total in terms of the product states? Because that is the meaning of change of basis. That's what a change of basis is. It's like you're writing basis state. You have a set of basis states, and you want to create a new set of basis states. So you want to write the new set of basis states in terms of the old basis states. That's what a change of basis is. Okay, so let's do that. And so what we're going to do is we're going to do that. I'm going to step through it for an example. Let's just describe what is the problem. I mean, so basically we have these operators, S total squared and S total Z, that we've defined, just the sum of the other guys. And then we want to, basically what we want to do is we want to find their eigenstates. Find their eigenstates. Because the eigenstates of these new operators form the new basis. That's what the new basis is. It's those eigenstates. And so how do we find those eigenstates? Well, one way, the brute force thing to do would be to simply diagonalize those operators. Just diagonalize them in the basis of the product states. Okay, so that's basically what we're doing. So we could just write the basis of the product states, and then we'd have to basically, to do this diagonalization, we would have to construct the matrices and then diagonalize them. Okay, that's the right way to do it. Brute force. I like brute force. Get a big computer, write everything down, diagonalize the matrix, get the eigenstates, then you're done. So that is in some sense addition of angular momentum. All right, that is what it is. Addition of angular momentum. It's just that. It's just, you know, we're just finding the new states. It's just the diagonalization of the total angular momentum operators. Okay, but we don't want to do that. It's very tedious. Nobody wants to do it. So we'll sort of use tricks. We want to understand the new basis. So the question is, what is the new basis of eigenstates of S total squared and S total Z? We want to know what those eigenstates are, but we don't want to go through all the trouble of calculating them all. And so we want to figure out what can we learn about those eigenstates by just being sort of clever. So so in order to, and so we're sort of cheating a little bit, but you know, but we have to, because otherwise it's just too complicated and just too tedious. So let's do an example. Let's do a simple example. We will do an example of adding angular momentum or spin angular momentum for 2 electrons. We will do the simplest case, and then we will generalize this to all cases. That's really being lazy. We will generalize to all cases. So we will do the simplest case, and then we will generalize to all cases. So that's being really lazy, but we are lazy. People are lazy by nature. So it seems like a very natural thing to do to me. So, okay, so let's do that. So let's consider 2 electrons, and then let's add their spin angular momentum. So the first thing we have to do is we start with the product states, because that's our starting basis. That's our starting basis. And then we will convert to the new basis. That's the whole point. That's what we're trying to do. But before we can convert to the new basis, we got to remember what the heck is the old basis. So let's consider the simple product states for 2 electrons. And so for 2 electrons, we have, we know that chi, the many body spin state for 2 electrons, is just going to be equal to, I have 2 electrons, so what's it going to be equal to? Someone tell me. For 2 electrons.
It would be S1 M1 and then times S2 M2.
Exactly, just a simple product state of the 2 electrons. That's exactly right. And so how many states are there? How many of these guys are there? Well, I'll say, you know, there's 2, and so here there's 2, and so then we see that we have 4 states. So let's write out those 4 states. And there's different ways of writing them out, but let's write them out. So let's do it like this. First, I could have one way of having it is I could have S1 M1 is equal to, for example, it's spin 1/2, and I could have it be plus 1/2. Or we know that it could be 1/2 minus 1/2. Like, these are the 2 possibilities, right? But of course, these are 2 very inconvenient to write, so we will just write it like this. So this state, we will call it spin up. Now it's for particle 1. I got to remember who I'm talking about. And this guy is going to be spin down also for particle 1. So when I write my many body state, So if I want to write, so I could write my many-body state. I could write it as, for example, if both particles have spin up, I could write it like this: up, particle one, up, particle one. So that's one many-body state. Another many-body state would be, I could say, another possibility would be particle one is up, but particle two is down, right?
Isn't the first one you wrote the, yeah, okay.
Yeah, sorry, I made a mistake. Okay, so, or I could do it like this. I could say particle one is down, and I could say particle two is up. Or of course I can say particle two is down, particle one is down, and particle two is down also. Okay, so we got all these possibilities. I'm sorry, let's make this a little better. Okay, so those are our four product states. I just written them out by brute force. But even this is too hard. Even that is too hard. So we'll use a shorthand. What we'll do is we'll say that we'll call this state up, up. And we'll call this state up, down. And we'll call this state down, up. And we'll call this state down, down. Now, this is real. People really use this notation. So this is an important notation. So, but when I write this like up, up, this is really important for you to realize that here I'm talking about particle number one, and here I'm talking about particle number two. So this is a real notation that people really use in the real world, but it's important for you to remember what the notation means. The first spin is referring to one particular particle, and the second spin is referring to the other particle. Because, remember, the particles are labeled. Even though they are indistinguishable particles, mathematically, I have labeled them. I stamp one of the particles with a 1, and I stamp the other particle with a 2. Even though they're indistinguishable particles, I have stamped them. In my mind, we are keeping track of the two particles. Otherwise, the math makes no sense. So, okay, so this is the spin of particle 1 and of particle 2. Now, here's something really cute to notice. So these are our product states. And so these are eigenstates of our old operators. Remember? These are eigenstates of S1 squared, S2 squared, S1z, and S2z. And you can see that. You can hit all of these product states with those operators, and you can see that these product states are indeed eigenstates of those operators. But what about the new operators? New operators. And the new operators are S total squared and S total z. Now let's take a closer look at S total z, because S total z, S total z is a really nice one. It's really simple. We love S total z. It's so simple because it's just S1z plus S2z in this case, right? It's just the sum of the z components. So I'm going to ask you a question. Are these guys, let me see where I should write this. Are the product states chi eigenstates of S total z? Are they?
I think so.
Well, yeah, they are. And the way to see that, if it's not obvious to you, and someone says to you, is this state an eigenstate of this operator? If it's not obvious to you, then what you should always do is just take the operator, hit the state, and see what you get. And if you get a constant times the state, then it's an eigenstate. And so you can so I suggest that you all do this. So we can just do this. We can just take S total z, and we can just hit S, what are we going to do? S1, M1, S2, M2, and so that's going to be S1Z plus S2Z hitting S1M1, S2M2. And so now when this guy hits this product, he's going to act on this. And so he's going to give us back H bar M1 times S1 M1 S2 M2, and then plus, and now when this guy hits it, he's going to act on this one, and he'll give H bar M2 times S1 M1 S2 M2, which equals, of course, H bar M1 plus H bar M2 times, actually, I'm going to skip a step, just I don't have to do it one more time. It's equal to H bar M1 plus M2 times S1 M1 S2 M2. Yay, we just proved it. So S total Z acting on the product state gives us this constant acting on the product state. So this then is the eigenvalue of S total Z. So every product state is an eigenstate of the S total Z operator. That's important. That's an important thing to remember. And it's really simple because the eigenvalue is just the sum of the two Z components. And that's really sort of intuitive because look at my fingers. I have, think of it classically. I have two spins and I have, two arrows with different Z components. And I add these two vectors and I say, what's the total Z component of these two vectors? You just add the Z components. It's like, it's duh. It's kind of obvious. Okay, so, but no. But of course, everything always gets more complicated in quantum mechanics because we have operators, blah, blah, blah. But sometimes things are not more complicated. Sometimes they stay simple. So here, then, let's do this. So I have M total, my eigenvalue of the Z, of the SZ total operator. And now I'm going to ask you, what is the total Z component of, what is the Z component of the total spin for this state right here, the up state? So what is it? Somebody tell me. What is the total Z component angular momentum? Spin angular momentum. What?
1.
Exactly. It's just 1/2 plus 1/2 equals 1. And now how about this guy? What is it? This guy now.
0.
Exactly, because it's plus 1/2 plus minus 1/2 equals 0. And what is it for this guy?
Also 0.
It's 0 because it's minus 1/2 plus 1/2 equals 0. And what is it for this guy down here? What is it for him?
Minus
-1.
Exactly. It's -1. Okay, so this is a cute thing to notice. These are the M total values. So what we've done is we see that in our old basis, we have 4 eigenstates, and we notice that those 4 eigenstates happen to also be eigenstates of the new operator, S total Z. That's very convenient. That helps us a lot. It tells us how to go forward. Because what we're going to do is, what we're doing is we're constructing the eigenstates of the new operators. So these are eigenstates. So this tells us then that the product states are eigenstates of SZ total, but they're not necessarily eigenstates of S squared, S total squared. They're not necessarily eigenstates of S total squared. And we want to construct the eigenstates that are eigenstates of both operators at the same time. So, so we got to figure out how to do that. So there's a trick. I'm sorry, let me keep an eye on the turn. Okay, so there's a trick, and the trick is to go to the top. We always do this, go to the top state. So the trick is, remember what we're trying to do is we're trying to find S total, M total equals what? We're trying to find these guys, you know, the total angular momentum eigenstates. How do we find them? So the trick is go to the top. The first thing we do, that's, you know, start at the top. Start at top. And in this case, the top, when I say the top, I mean the product state with the most S sub Z. So biggest M total. Go to the top. And in that case, so which state is that? Here. The top is, well, I mean, it's kind of obvious. It's the one at the top. It's up, up. Okay, this is the top right here. That's the top. And so we ask ourselves, so we go to the top and we ask ourselves the question, is this a an eigenstate of S total squared? So we go to the top and then we ask, is it an eigenstate of S total squared? And if so, then what is the value of S total? All right, so now to answer that question, we use some sort of linear algebra logic. So we look at this state and we notice that it has M total equals 1. And so I will ask you, could it be an eigenstate? Could it be an eigenstate of S total equals 2? Actually, I'll ask you a simpler question. Could this state be an eigenstate of S total equals 0? Yes or no?
No,
Why not?
because it doesn't, then our M is larger than S. We know like M values are restricted between negative S and positive S.
Exactly. And so if my total spin angular momentum is 0, then the highest M total is 0. And this guy has M total of 1. So he cannot be S total of 1. So S total does not equal 0. Okay, now I'll ask you, how about S total equals 2? Could this be an eigenstate of S total equals 2? Now, in principle, you might say, well, sure, because S total equals 2 could have an M total equals 1. But when I look at my manifold of states, do you see any values of M total equals to 2? Yes or no? Yeah, there aren't any. There's no M total equals 2. Now, the thing is, if I had a state that had M total equals 2, I could always hit it with a lowering operator, and then it would have M total equals 1, M total equals 0, minus 1, minus 2. So basically, the fact that there's no states that have M total equals 2, that means that there are no S total equals 2 states in this manifold. So they don't exist. So this guy so there are no S total equals 2 states because there's no M total equals 2 state. So there's no S total equals 2, there's no S total equals 0. And so this state, this top state, has to be S total equals what? Somebody tell me.
One.
Say it again.
1.
Yes, it has to be S total equals 1 because because that's the only choice that's left. So I know that this is maybe not like, you know, the most satisfactory proof from your point of view, but it's actually rock solid mathematical logic if you think it through. But even if it seems a little fluffy right now. So the point is that we went to the top and we saw that this state up is then it has S total equals 1 and it has M total equals 1. So it is an eigenstate. It's an eigenstate of S total squared and S total Z. Now to see that it's an eigenstate of S total squared, you could do, to see that it's an eigenstate of S total squared, we could check. We can check that, because we did this very sort of wishy hand-waving kind of mathematical reasoning to see that it has S total equals 1, but we can now check it more rigorously. Check that it's eigenstate of S total squared. So we can do that because we can do this. Look, we can take it and we can take the S total squared operator and hit it against the state up. And we want to see that for it to be an eigenstate, we need it to be constant times up. And in fact, it shouldn't be any constant. It should be a particular constant. It should be h bar squared times what? Somebody tell me, what's that constant? What should it be if it's truly an eigenstate? What should that
2?
constant? Yeah, exactly. 1 S total times 1 plus 1. That's right. Times up. That's right. That's what we want. But we can check that this really works because we can do this. We can say S total squared is S1 plus S2 squared, which is S1 squared plus S2 squared plus 2 S1 dot S2. Now, these guys are easy. When these guys hit up, it's going to be easy. But when this guy hits it, it's going to be hard. So that's going to be a pain in the ass. But let's just do it. Like, so if I do, like, for example, if I hit S total squared times up, then that's going to be, let's do it, S1 squared plus S2 squared plus 2 S1 dot S2 acting on up. Now, S1 squared acts on state 1. So what does S1 squared turn into when I do this? Because remember, this is particle number 1 and this is particle number 2. And remember, this particle number 1 is representing, that arrow is representing S1, M1, and this guy is representing S2, M2. So when S1 squared hits this thing, what does it give me?
3/4 h squared.
Exactly, h bar squared times 1/2 plus 1. That's right. When this guy hits this, he's going to act on that second guy. What's he going to give me? When this guy hits him, what's he going to give me?
Just the same value.
Exactly. H bar squared, 1/2 times 1/2 plus 1. But when this guy hits it, it's confusing because these states are not eigenstates of S1 dot S2. So there, it's not easy. So that's the hard part. S1 dot S2, up. Okay, so that's what we get. So these guys were easy, right? These guys were easy, but the dot product part is hard. So to do the dot product part, we got to do this. We got to we got to do this. We got to say S1 dot S2 is equal to S1x times S2x plus S1y S2y plus S1z times S2z. And we got to stick these guys into there. Now, if I do that, you see that these guys are easy because when S1z hits that, S1z is going to turn into what? When S1z hits this, what's S1z, the operator, going to turn into?
H over 2 or H bar over 2.
Exactly, H bar over 2. And when S2z hits that, what's it going to turn into?
The same value.
Exactly. But these other guys are hard. And so to deal with S1x and S2x, we gotta, you know, it's more work, but I'm sort of showing you this because this is how you do spin algebra. So we got to mess around. So to deal with the Sx and the Sy, we got to use this. We got to remember that Sx is equal to 1/2 times. Does anybody know what trick I'm about to use? Can you guess?
Ladder operators.
Exactly, raising and lowering. Sx is equal to 1/2 S plus S minus, and Sy is going to be 1/2 S plus minus S minus. Is there an I in there? Oh yeah, there's a little I in there. S minus. Okay, so I can write Sx and Sy in terms of raising and lowering operators. And so then we can, using the little formulas, we can remember that, for example, if we hit, let's see. Well, okay, so you can remember, then using this, you can show that Sx acting on spin up is equal to H bar over 2 spin down. And you can see that Sy acting on spin up is equal to H bar, Sy acting on spin up is equal to minus H bar over 2I times down. And so using this knowledge, and we got this from the raising and lowering operators, that those formulas that we showed before, you can then plug this all into here, and then you can show, and I'm not going to go through it, but you can show that S total squared acting on up is equal to, and I'm going to skip a few steps, you know, do the work at home, but the answer you'll get is that it's equal to H bar squared times 1 times 1 plus 1 times up. Because you'll get some cancellations and whatnot. You just have to do the work. And so therefore we have just shown, we've proven that S total equals 1. So therefore it's an eigenstate. So that means that up is an eigenstate of S total equals 1 and M total equals 1. Okay, so and this is always the case when you're adding angular momentum. You always go to the top, and then you always find that that top one is always an eigenstate both of S total Z and S total squared. So now we want to get the next eigenstate. So this means that what this is telling us is that this is telling us that what we have gotten now is we've gotten the state S total equals 1, M total equals 1 is equal to up. Okay, so what's the next state that we want to get? How do we get the next one? Because we're constructing the new basis. Does anybody have an idea for how to get the next one?
Apply a ladder operator?
Exactly.
Lowering operator?
Exactly. Because we know then that we should be able to get S total equals 1 m total equals 0 should be proportional to the lowering operator, s total minus acting on 1, 1. That's exactly right, because we just act the lowering operator, and it should lower it by 1. So then let's do that. And so because we know that 1, 0 is proportional to s total minus acting on 1, 1. So let's do it and find what this new state is. And so we'll do s. So s total minus will be s1, because remember that s total minus is equal to the sum of s1 minus plus s2 minus. That's the definition. And so if we act on these guys on the state up, up, then we're just going to hit. So this guy is going to lower this guy, and this guy is going to lower that guy. And so this is then going to result in, I'm going to get, when this guy hits that guy, it's going to result in, it'll be h bar down, up. And when this guy hits that guy, it's going to result in h bar up, down. Okay, because this guy is lowering this guy, whereas this guy is lowering this guy. And so when I multiply that out, this is what I get this. And so this is equal to h bar times down, up, plus up, down. And so I see that this then is proportional to the state 1, 0, where that's s total and that's m total. And so then I can just normalize it. And so we can just do a simple normalization, just find the length of this vector by squaring it with itself. And so then after normalizing, which is easy, then we can see that the state 1, 0 is equal to this guy normalized. And when you normalize him, you get a 1 over square root of 2 out front. Oops. Down, up, plus up, down. Okay, we did it. We constructed, so now we've constructed another basis element. See how we're constructing the new eigenstates one by one. And so so what we have now is we have 1, 1, and we've constructed 1, 0. And what's the next one that we can construct?
1 minus 1.
Exactly. The next one is 1 minus 1. Because we know then that 1 minus 1 is proportional to s total minus acting on 1, comma 0. And so then that's what we got to do. So then we see that 1 minus 1 is proportional to s1 minus plus s2 minus acting on this guy, 1 over square root of 2 times down, up, plus up, down. Okay, so, and we can do it. It's just a bunch of algebra, but you can see how you do it. You just go through it. And when you go through that algebra, you'll find something very cute. You'll find that 1 minus 1 is equal to does anybody know the answer? I mean, it's not obvious by doing the math, but by using clever reasoning, you can know the answer. What's the answer? Does anybody know the answer?
The 2 down state.
Exactly. If you go through all the brute force math, then you'll see that it's down, down. And if you think about it, you'll realize it had to be down, down, by the same reasons that the up, up was the 1, 1. So, okay, so that's really nice. Okay, so now what we have then is we have these 3 vectors. We have 1, 1, 1, 0, and 1 minus 1. But the thing is that we have that's only 3. And when we had 2 spin 1/2 electrons, we noticed that there were 4 states, and so we're missing 1. So let's go way back to this beginning. So we go back to the beginning, and we realize that the product states here right there, these product states, we had 4 product states, but now we only got 3 of the total angular momentum states. We're missing 1. Which one is it? Well, there's a giveaway, because when we look at our new total angular momentum states, the ones that we got were 1, 1, 1, 0, and 1 minus 1. And so we see that we got an M total equals 1, we got an M total equals 0, and we got an M total equals minus 1. But when we look at our product states, we see that we have an M total equals 1. We have that's the M total. The M total equals 0. And we have an M total equals minus 1. Exactly the same. But for the product states, we have 1 additional state that has M total equals 0. So so basically, we have 1 more state that has M total equals 0 that we did not account for. So what is that state?
Spin total equals 0.
That's exactly right. It has to be, because there's no other states for spin total equals 1, because 1 only goes to 1, 0, and minus 1. There's no more. We got them all. And we know that there's no S total equals 2, because otherwise there would be M total equals 2, and they're not there. And there's no S total equals 3, because they're not there. So none of them are there. The only one that it can be is this one, 0. Because if I have S total equals 0, then the M total has to equal 0, and there's only 1 of them. So that's the missing one. Okay, so how do we find it? Well, we are constructing eigenstates. We're constructing eigenstates of the S total squared and S total Z operator. These are Hermitian operators. And so we know that the eigenstates all must be what? Can you remember a property of the Hermitian?
Orthogonal?
Yeah, exactly. Hermitian operators, remember the eigenvalues are real and all the eigenvectors are orthogonal. So the trick then, it's like a linear algebra trick. The trick is to go back here and to notice that here I have S total equals 1 and M total equals 0. This is an M total equals 0 state. And so we must be able to construct another M total equals 0 state. And if we are able to construct it, then it has to be orthogonal to this one. So we can just ask ourselves, what is a state that's orthogonal to that one? So I'll write it like this. So we know that 0, 0 is perpendicular to 1, 0, which is equal to 1 over square root of 2 up, down, plus down, up. So we know that the state we're looking for is orthogonal to this one, because, and this has two elements, right? It has two parts. So what is another state that's orthogonal to this one? Can you guess? We basically have to construct a state that's perfectly orthogonal to that one. But also a state that has m total equals 0. What's another m total equals 0 state that's orthogonal to that one?
Just have a minus sign instead of a plus.
That's exactly right. Because we have these two, we have two product states in there, and so that means we should be able to write the sort of the symmetric and anti-symmetric combination there. You know, if I have two states, then I should be able to write up, down, minus, down, up. And that's it. That's the one. That's the answer. And of course, you can check. You can take the S total squared operator and act on this new state. And I'm not going to go through the algebra. I want you to do it. Check on your own by actually doing this algebra. But when you do that, you see you'll get 0. And then if you do this, if you hit it with SZ total, acting on that, then also you'll see that you get 0. And so I want you to do that on your own, and then you can see that it works out, that you get that it's an eigenstate of these two operators. Okay, and so all right, and so now we see that we have these eigenstates, and so we've constructed these eigenstates, and I'll write them down. We have we took a spin 1. We took 2 spin 1/2 particles, and we created an S total equals 1 manifold, which was up as m total equals 1, and then we have 1 over square root of 2, up, down, plus, down, up, has m total equals 0, and then we have down, down, has m total equals -1, and then we have our S total equals 0, which is 1 over square root of 2, which is up, down, minus, down, up. And so, and this is also has m total equal to 0. And so, okay, so we did it. And what we've, and we call these states, we have a name. We call these the triplet. Because and the reason is because there's 3 of them. So these are called the triplet states, and the triplet states are S total equals 1. So the triplet states, this is so famous, such a famous result. When you have 2 spin 1/2 particles, if you add them together, and if you get spin S total equals 1, then those are called triplet states because there's 3. Whereas the S total equals 0, we often call the singlet because there's only 1. And that's the one where we have S total equals 0. So we call this the singlet state. So this is a spin state that has S total equals 0, whereas these 3 states have S total spin equals 1. So that's how you do it by brute force. Okay, so we constructed the new basis by brute force. You know, we just went in there and we just made it. We built it. But of course, that's quite tedious. No one wants to really do that. You know, like if I gave you like 5 spin 1 particles and I said, what is the total angular momentum of 5 spin 1 particles and what are all the states? It'd be too hard for you to construct all this. So there's tricks. So what we do then is we notice that there's a pattern, and you could derive this pattern using a process of induction. a very long, tedious mathematical proof that I will not go through. But through a process of induction, we can find the rule. Process of induction leads to a rule. And let's talk about the rule that we get for adding angular momentum. Rule for adding angular momentum. And the rule that we see is that if we are adding two particles, S1 plus S2, two particles we have spin S1 and spin S2, then when we add them together, the total spin can equal S1 plus S2, or it can equal S1 plus S2 minus 1, or it can equal S1 plus S2 minus 2, all the way down to the bottom limit is S1 minus S2, the absolute magnitude. That's the rule. And so then these states, product states, if I have two spins and these are product states, which I can represent as S1 tensor product S2, but then these are total angular momentum states. And this is the rule. And this is really important. And so let's just take a look at what I mean by that, because we just did this. So let's look at this rule. We just added S1 equals 1/2, S2 equals 1/2. We just did that. So let's see if the rule works, because we saw that spin 1/2 tensor product with spin 1/2 leads to 4 product states, right? 4 product states. And so now let's do this new rule, and we see that we have S total is equal to, okay, what's S1 plus S2 here?
1.
1, exactly. And then we can go, then we have to do that minus 1. So 1 minus 1 is 0. And then we keep going down. 0 minus 1 is minus 1, but we only go down until we go to the difference. And 1/2 minus 1/2 is 0. So then we're done. We're stopped. Okay, we're done. And so now let's look at this. So now let's do some counting. And we see that if I have S total equals 1, how many states do I get from S total equals 1? How many states?
3.
3, exactly. It's a triplet. It's 3. And the rule is, remember, it's 2S plus 1, right? Because if I have a state that has S, MS, then we know that MS has to be less than S, or less than or equal to, it goes all the way from plus S to minus S, and this leads then to 2S plus 1 states. And so then here, if I have a singlet, then how many states do we get?
Wow.
Exactly, because 2S plus 1 is 1. Right. And so if I add them up, 3 plus 1 equals 4. Yay, it worked. But let's keep going. Let's do another example. Let's consider an example of, let's do a different example. Let's just pick one. Suppose I had S1 equals 1, and I had S2 equals 3. What happened? What if I had one particle of spin 1 and one particle of spin 3? Just some arbitrary thing. So the product states, I would have spin 1 do the tensor product with spin 3. And so how many states would I get? How many spin 1 states are there? How many spin 1 states are there? The rule is 2S plus 1.
3.
Yeah.
3. How many spin 3 states are there?
7.
So how many states do I expect? How many product states do I expect? What?
21.
Right, 21 states. Okay, somebody has doing feedback. Somebody has to mute themselves. There's some weird feedback. Okay, good. Now let's add them and let's use our rule because I want you to see a really cute little rule. So if we add them, then we have S total is equal to the total. So remember, I do S1 plus S2. So that's 1 plus 3 is 4, right? And then I keep going down. I do. Remember the rule. Let's see. Here's the rule, right? It's this rule: S1 plus S2, S1 plus S2 minus 1, all the way down to the difference. So what's the next possible one?
3 and then 2.
3.
And then,
2.
2.
and are there any more?
No.
That's right. There's no more because that is the difference because 3 minus 1 is 2. So that's the bottom. So these are the possible total angular momentums you can get by adding these angular momentums. And then this, and let's count them. So how many states have spin 4? How many? Remember, it's 2s plus 1. 9, that's right.
And then
And for
7.
3, it's 7 and 2
5.
times. That's 5. So now let's add it up. 9 and 7 is 16 plus 5, 21. Okay, I want you to see that it's a basis transformation. So when you change basis, you always have the same number of states. And so, so we got to end. So I just want to write down the last thing in general. This is so in general. So let's now write it as a general formula. General formula. If we want to find, and this is the last thing, if we want to find the state S total, the total angular momentum state from the product states, then we have to, what we have to do is we have to do a sum over all the product states, but a subset. The product states have to have their Z component add up to M total. So I add up all the product states, S1, M1, S2, M2, but what is the weight of the different product states? The weighting, well, to get that weighting, there's a constant here that we need to know. And that constant is going to depend on S1, S2, S total, and it's also going to depend on M1, M2, and M total. And this is what we derived today. We actually brute force figured out what these constants were for the simplest case. But in the most general case, it's hard to find them out. And so what you do is you look them up in a book. Nobody actually derives them. And these constants are called Clebsch-Gordan constants. Clebsch-Gordan. So what we did today was we calculated the Clebsch-Gordan constants for adding spin 1/2 and spin 2 spin 1/2 particles. But in general, you would look these up in a book. Okay, folks, that's it. Thanks a lot. Bye-bye.
Thank you.
Thank
Bye-bye.
you.
Thank you, Professor.